All right, in Unit 1 and 2, we looked at something called kinematics, which is really just mathematically describing how objects are moving around in space, like velocity, the distance they cover, the rate of change of their velocity, acceleration. And in Units 3 and 4, we start to look into this new concept called dynamics, which are when forces, we're looking at really into why objects move the way that they do. And this is caused by forces. So Unit 3 was looking at linear forces, and we began the unit by then looking at Newton's 3 laws. So the first law says that an object at rest stays at rest, or an object in motion stays in motion unless an unbalanced force acts upon it. Newton's second law says that the sum of those unbalanced forces, or the net force acting on an object, causes the mass of that object or system of objects to accelerate. So really, mass is also known as inertia, and really is your resistance to your acceleration. So if the mass is really big, then it takes a greater force in order for you to accelerate. And so we have F net here, or we have the sum of all forces. And remember that this is a system. A lot of times we're just dealing with one object, but we can also have a system of objects where you have maybe two things that are attached by a pulley, and the pulley is moving, and so both of the objects move. So we just have to keep in mind that whatever is accelerating would be the mass. And then the last law says that all forces have an equal and opposite force. So if you apply a force on something, it pushes back. So if I push on the wall pushes back on me with an equal and opposite force. So let's tie this into the graphs that we were looking at in the last couple of review videos, where we're actually talking about distance versus time and velocity versus time. So remember that now we're dealing with the terms of saying like something has a net force. So if a net force is acting on an object, that means that yes, the object is accelerating. So a distance versus time graph for an object that has a net force on it would be the same as a distance versus time graph for a displacement versus time graph for an object that is accelerating. So in this case, we would see a curve so that the slope of the line tangent at any point is changing, and it's actually increasing, and that's where we're going to see that acceleration. Whereas if we had something that had no net force is either going to be in what we call static or dynamic equilibrium. Static equilibrium is when you're not moving at all. So in this case, the distance over time graph would look like this, where you would have a slope that would be equivalent to 0, and you're sort of plotting the same position every moment. You're really at rest. And then we have an example here of dynamic equilibrium, where when you're in dynamic equilibrium, you're going at a constant velocity, so you're not accelerating in either of these instances, but you're going at constant velocity, and therefore you would have some sort of line here, and the slope of that line would be the velocity or the constant velocity of that object. Right? So then if we were going to look at the velocity versus time graphs for those, so velocity versus time graph here for something that's accelerating, remember the slope of the line is going to be the acceleration here. So we'd see something like a line, and we would know that this represents a net force. Whereas when something is at rest or the velocity is 0, we would have a graph like this. Or if the velocity was something that was constant and non-zero, we would have a graph that looks like this. But again, these two would indicate no net force, and this would show a force. Right? So then I taught you rules for solving really any Newton's law problem that will continue on as we go through the rest of the review videos. The first step was to draw a free body diagram, right? And free body diagrams, we have some rules. Free body diagrams are only going to show forces that are acting upon an object. The object is represented by a dot or a box, and the arrows are going to originate from that dot or box and point away from it and be in contact with it. All forces are caused by touching and by contact, right? So it's a push or a pull on the object. So really you just have to look at it and say, what is touching this thing? Whatever's touching it must be acting or must be exerting a force upon it. There are two exceptions to this rule, which are our field forces, and those field forces are the force due to gravity and electric force. So both of these forces will exist without something coming into contact with it, so we can't forget those. All right, so if I was just gonna have an object, say, being pulled up by a string or being dangled by a string, or maybe something just resting on a table, some of our basic free body diagrams where something is in equilibrium is here, right? So here for the string scenario, I've got FT and I've got FG, right? FT pointing up and FG pointing down. For a book sitting on a table or something resting on a table, you've got normal force and we have FG. And so the arrows are roughly the same length. And when the arrows are the same length, that is showing that the thing is in equilibrium, right? So there is no net force happening and there's no acceleration. And like we saw on the graphs, static means that the object is actually at rest and the velocity is equal to 0, whereas dynamic means that something is going a constant velocity. But again, remember that there's no net force in one direction or another. So make sure on the AP exam, when you're drawing free body diagrams, you follow those rules and you have a dot representing the object. You have the arrows pointing away or originating from the object, coming into contact with it, and also showing relative lengths of things. So if something has the same force up and down, make sure that the arrows look about the same length. Whereas if something has a greater force up than down, so this one looks like it's a little bit shorter than the top one, that you can show a scale. All right, so that's the first step to any Newton's law problem, is to draw those free body diagrams. So draw a good free body diagram demonstrating those forces. Then the second step is to ask yourself, is this object accelerating based on the parameters of my problem? If the object is accelerating, then we go this direction and we use Newton's second law in order to then to figure out something about the problem, right? So the net force, or the sum of all forces, is equal to the mass of the system times acceleration. So in the case of this one, where we have some sort of acceleration, you can see like the up arrow is longer than the down arrow. So in that case, I would say Ft minus Fg is equal to Ma. And keeping in mind that that mass of the system is everything within the system. If, for example, the object is in equilibrium, as in this picture where the up arrow and the down arrow are equal, or the object is at rest or not accelerating, then the answer to question 2 is no, it's not accelerating. And then we just go to equilibrium expressions, where everything up must be equal to everything down, or everything to the left must be equal to all of the things to the right, and that knowing that they balance out. So in this case, we would know that Fn is equal to Fg. All right, now the next thing, or the last thing really in this video that I want to talk about, is some specific types of forces that we mentioned, and trying to identify like how to compute them, right? So one of the first forces that I've already talked about and we've written down here is the force due to gravity. Let me grab a pen here. So we've got the force due to gravity, or the weight of an object. So we have Fg, and this is also known as weight, right? It is the force due to gravity. It is not acceleration to gravity. It does not equal 10, right, meters per second squared. If the object is 1 Newton, then or if the object is 1 kilogram, then yes, it could be 10. But a lot of people start wanting to use, say, like 10 meters per second squared for Fg. But remember, that is acceleration due to gravity, or little g, right? And it is equal to mass times acceleration. So in this case, we've got mass times gravity. Right? Now, another force that we commonly use and we've seen already is the normal force. Right? Normal force really is how hard something is pushing into a surface, how hard something pushes into a surface. Right? And in this case, how hard something pushes into a surface is going to be perpendicular to that surface. So if you just have an object sitting on a level tabletop, then the normal force and gravity would be equal to one another. Whereas if I tilted it up on its side, the normal force is going to be a little bit less. It's not pushing into the surface quite so hard, and it would be in this direction. So normal force is also always perpendicular to that surface. All right. It is also what a scale would read if you're just sitting still. So it's what a scale reads, right? But it also will be, well, it reads your weight if you're just sitting still, but if you're accelerating, like the scale would actually change, right? So normal force really is what a scale reads. It's also your perception of your own weight. So you feel your weight because you're pushing down into the seat that you're sitting on. So if you feel weightless, then that doesn't mean that your weight is really zero like it is over here. Like over here, it doesn't mean this weight is actually zero. Weightless just means that the normal force is equal to 0. You feel like you don't weigh anything. Right? So that's normal force, right? And in this example right here, we're talking about one box, and it's at rest here or it's at rest here. But also, keep in mind is how hard you're pushing into a surface. So if I were to come and apply some downward force, like if I were to push down with my hand, it's going to push into the table more, right? So it's going to be equal to every downward pushing force that's perpendicular to that surface. All right, let's look at friction then. Actually, let's do tension and spring force first, and then we'll come back to friction because there's a little bit more to friction. All right, so Ft is called tension, right? And it's a force that's exerted within a string or experienced within a string or a rope or a cable, right? Most often, we're going to be dealing with tension as, transferring force from one other object to another object, and we're thinking about the string as having some sort of negligible mass. The tension within the string is going to be the same, experienced the same throughout in a lot of those instances. However, we did see a free response where you had a string that was hanging like this vertically from the ceiling, right? And we were looking at what the tension is at different points. And because the mass of the string is at different points here, like if we were to pick this point or this point or this point, like the free body diagram for the part of the string right there would be the tension up and the gravity down, right? Whereas this would be the tension up and the gravity down, the tension up and the gravity down. But higher you up in the string, you're going to have more tension because there's just more weight of the string down towards the bottom. Right? So that's an example if the string didn't have a negligible tension. But a lot of times we're just going to be dealing with objects that where the string mass is negligible, right? And it's just connecting two things, or it's being used to apply a force essentially. Right? Then we also have this idea of spring force, which we really didn't talk about in this unit, but it came into play later and it is used a lot in Newton's laws sort of problems. So spring force is equal to K times X, and this really is negative KX because all it means is like if I have a spring right here and it's just sitting there, if I were to pull on it in this direction, the spring pulls back. Right? And so the amount of force that it takes to sort of displace a spring is called the spring force. And K is the spring constant. It's really the newtons per meter that it takes to move it. So if the spring constant's 20 newtons per meter, it means that it took me 20 newtons to stretch this thing a meter. And X is the change in length of the spring from its like natural length. Okay, but again, we'll come back and talk about that a little bit more when we start going into elastic stuff. All right, and then the last force that I want to mention in this video is friction. So the force due to friction, right? And the force due to friction is calculated by two different factors, or it's affected by two different factors. One is a property of the surface, which is called the coefficient of friction. It's a mu. It looks like a cursive U. So coefficient of friction. And then we also have the normal force, right? Which is how hard you are pushing down into that surface, right? So there are two different types of friction. There is static friction and there is kinetic friction. So static friction is when something's at rest, right? Preventing something from moving. And kinetic friction is when something is moving along, right? So static friction is always going to be greater than, or the coefficient of static friction is always going to be greater than the coefficient of kinetic friction. So the coefficient of static friction is greater than the coefficient of kinetic friction, which means that it's harder to get something going than it is to keep it going, right? So let's just look at an example of friction, right? So I have a box and it's on a table. And remember, the first thing that we do is we draw a free body diagram. So let's just say that I'm pushing it along and it's going at constant velocity, right? Well, here's some applied force. Friction is always going to oppose the direction of the motion. So this would be friction. And then my other forces are going to be normal force, and this is going to be the force due to gravity, right? So I said it's going at constant velocity, so our second question when we're doing Newton's Laws problem is it accelerating? And the answer then would be no, so that I know that this force is equal to this force, and this force must be equal to this force. So if I wanted to know what the force is that I'm applying, I would just say, okay, well, I know that the applied force is going to be equal to the frictional force. And the way that I actually calculate friction, given the parameters of a problem, are that the coefficient is equal to, that the coefficient times the normal force is equal to force friction. And because this thing is sitting on a flat surface, Fn is equal to Fg. And we know that Fg is mg, so we basically get that we can find the applied force just through all of these like equivalencies, that it's equal to mu times m times g, right? Now, if the object were accelerating, so this is for a constant velocity, like let's say the object was at rest. If the object was at rest first, then we would do the same exact thing. The only thing that would change is that the coefficient would be different, right? It wouldn't be the coefficient of kinetic friction, it'd be the coefficient of static friction. And notice I left the mu and the s off because it really mathematically comes out to be the same way of calculating things, whether or not it's constant velocity or it's static. Right? Now, if that object were accelerating then, so if there was some sort of acceleration, then instead of doing using equilibrium expressions, now we're going to use the sum of all forces equals mass times acceleration. So I would say that the applied force minus the force due to friction is equal to the mass of the box times A. And then I would just do exactly what I did up here before and just perform a bunch of substitutions until I get the variables that I want. Okay. One last thing before we get going. Remember, if you are to put something on an inclined plane, so remember that normal force is always going to be perpendicular to the plane. So this would be my normal force, whereas gravity is always down towards the center of the earth. So it would be straight down. Right? Friction is going to oppose the motion of the box. So the box wants to slide this way, but the friction would be up the hill. Friction would be up the hill. And this would be a good free body diagram for this scenario. Remember, we don't put components on free body diagrams when we do it, but I'm going to draw them in here so we can kind of see. So in this instance, you have the normal force would be equivalent to the component of gravity that's down, whereas the other component is making it want to slide down, and these angles are the same. So this side right here, this of that right triangle, we're going to use cosine for that. So FG cosine theta, and this one would be FG sine theta. All right, so force normal is equal to FG cosine theta when you're on an inclined plane. FG sine theta is what's making you want to slide down the plane, and then we'd have to see how does that relate to friction. And then we also derived out that we could figure out the coefficient of static friction for something on an inclined plane by taking the tangent of theta. Right? So again, this is an oversimplification of the things that we did in terms of friction and sum of all forces, but gives you enough of those little tricks and tips that hopefully we can solve any of these linear forces problems. So in the next video, I'm going to talk about what happens when things start to move in circles.